Good morning. We're into our third or second lecture. It's the second one, right? Or third? Yeah, it's the third. The weeks are going by quickly already is what I feel like. We'll get caught up in this class in terms of the days and everything later in the semester. So, like I said before I turned on the video, I've got papers from everybody. I think the Slack seems to be working for everybody in all of my classes, actually, including Capstone Design. I did quite a bit of work last week with that. I spent a half a day in presentations, and I'm coaching one team. So we iterated on their slides. I've got the solutions posted. I see a typo down here. I need to say hints number 2, which will be coming up soon, but that blurb should be taken off of here for right now. I know I had you do things in the homework that were random variable things that we had not actually talked about, but because it's review, I don't have my mind, I don't have a problem with it, and nobody brought up any issues with me. We are going to continue to review through, and then we'll get into random processes. And if you've been looking at next assignment, and if you haven't, we'll look at it later. It does have a simulation in it, though, so you are going to get a chance to do some modeling and simulating. And I don't know between you two and number 3 whether you've ever had random processes. Did you have random processes? So you're probably ahead in the way we teach things here at UCCS. So did you ever do a random process simulation where you just modeled an ensemble to just kind of play around with the idea?
Not yet.
Okay, that's what I'm going to have you. That's what I'm going to have you do. It's a problem that's in the book, but it's interesting because it gives you a better understanding of what the ensemble is. So I'll be talking about this more later, but it'll be an ensemble of waveforms, and whether you did it in MATLAB or Python or Julia or whatever, the way you'll set it up will be very. At least the way I want you to set it up is a matrix will hold the ensemble of waveforms, and each row of the matrix will be one waveform, and then the next row will be another ensemble, and then you'll be able to do sample statistics, either slicing vertically or horizontally, and then kind of relate the things that we'll be talking about later today, the statistical averages and the time averages and how they relate together if you've got a stationary process or White's stationary, and then you'll get a chance to understand the definitions better. So I like it a lot, just because you got to start somewhere, and sometimes the concepts do get confused. So the thing we left off on was joint CDFs and PDFs, and we'll be using those things definitely in modulation theory. So to get ourselves started, we talked about joint probabilities. Now we talk about joint random variables, or joint PDFs and CDFs. So here are the formal statements. A joint CDF is the probability, if you want to replace the capital F there by the probability sign P, probability of an event that, I don't know why I have F in here. Probability random variable x is less than or equal to little x, and y is less than or equal to little y. Then if you take the derivative, partial derivative in both coordinates, you get the joint PDF, and then you can integrate back from the PDF to get the CDF. We'll be looking at a few examples here. By the end of this chapter, which will happen around the break time, I'm hoping we'll be into n-dimensional random variables. Just a brief introduction, and then we'll jump into random processes. So properties, there's 2 properties on the bottom of this page, and then there's more on the next page, but it just so happens that these first 2 properties also form the existence requirement for a joint PDF, namely that it be a non-negative function and that the volume of the function be 1, just the extension of the one variable case. Other properties are, though, that you can get the probability of lying in a region. In this case, it's a rectangular region. By just integrating the joint PDF over that region, you can get back to the marginal, as it's referred to in probability theory, marginal CDF, by just limiting out the CDF in the unwanted random variable. So if you want to get the CDF on X, you just take the joint CDF and rail, this is my way of thinking of it, rail the Y value all the way out to infinity, which ensures that it has certainly occurred, and then you were getting what's called the marginal. And does anybody in here have a good definition of why we have the term marginal versus joint? I'm just curious. Did you ever learn that earlier? I don't have a clear answer either, but I have an answer that I'm recalling from my memory from one of my professors years and years ago. No? Okay. My understanding is marginals have something to do with keeping records and having, like, the tally in a column on the far left or a row across the top. And that would be then the term marginal, because they're sitting in the margins, either the far left or far right, I guess, and then across the top. And then, so you would be summing the rows or summing the columns if you were having a discrete joint probability, and those would be the marginal probabilities. I guess I could do a Google search on it. I'm just, there's things that are in the language that I will say marginal because it's just sort of in my head, but I think there's a reason for that historically. At any rate, we have a way of getting back to a marginal CDF, so we have a way of also getting back to a marginal PDF by just integrating out the unwanted random variable. And we'll see how this extends to conditional random variables and pairs and different combinations when you have n random variables right at the end of the chapter. Okay, so here's just a simple example to just kind of go through the existence in 2 dimensions and then look at some things. So here's a function that is sitting in a tile, and I'm going to look down on the floor for a second and see what do the tiles look like in this room. They're not a solid color, they're different colored tiles. I actually don't know how it's laid out, but this PDF sits on a tile that's 1 by 1, and there's a change in elevation as you go across the surface of the tile, and that forms a non-negative function. And then there's this arbitrary scale constant A, which is thrown out in front as something that you have to find to ensure that the volume of the joint PDF over that square tile is exactly 1. So you just integrate it, and that's what I'm doing down here, integrate it, and then find out, yep, A equals 1, we'll do it, because that will make the volume equal to 1. So a long time ago, I was using Mathematica a bunch, and this was a picture that Mathematica drew for me. So that's what the PDF looks like. It looks like if you were to walk over the PDF, you'd be walking on a tile that's tilted up towards the 1, 1 coordinate direction. And if you want to now just verify the form of the CDF, and then we can talk about a property that the CDF has to have, we can go ahead and integrate it. So what we're going to do right now is just simply go through, let's see, just simply apply that definition to go back to the CDF from the PDF by integrating. And it's a little bit trickier. This seems like a really mundane, simple problem, but when you go to integrate it, you've got to break it up into cases when you do that. So if we ensure that X and Y are in the interval of support for, or region of support for the joint PDF, we can then just integrate from 0 to X and 0 to Y. The order doesn't matter. It's rectangular. it's separable, things like that from the integration standpoint. So there's the function, x squared y plus xy squared over 2. And then if we want to consider y greater than or equal to 1, so we're not going to constrain it, then we have we have to limit the y variable of integration to stop it at 1, and then that gives you the CDF for that region, and then likewise the other region going off in the other direction where x goes greater than 1. And then finally, where both x and y are greater than 1, so you're outside the squared tile and you're just moving out in that space where x and y are both greater than 1. And then if you draw the picture again, you've got these regions that are showing up. When both x and y are less than 0, then you're sitting on the ground floor. You're sitting at 0 in the region. I'm not really good at drawing that necessarily. That's the region where they're both active, and that's where you've got the parabolic shape, because you've got an x squared and a y squared in there. And then if you go off to either of the two sides, you get that region where just one variable is active and the other one has been limited to its value of 1. And then, of course, the plateau is at the top. So I don't know if this is exciting at all, but I like hiking, and I hike trails to the tops of mountains at times. I haven't done that too recently, but I used to be really enjoy backpacking. I just haven't gotten out for quite a while now, picking the right weekend and so on. But one of the things about a CDF is that it's monotonically increasing, so, or non-decreasing is what I meant to say. As long as you're walking on the CDF anywhere, you're going to either be holding constant or climbing. And then if you hit the plateau, then you hit the plateau. But I guess the thing about the CDF that I think about, if that was the surface that you were always on when you were on a trail, you would never complain, because if you know you got to go to the top of a mountain and you have a sub-peak and then you have to go into a saddle and then climb some more, it's like, I did all this climbing, I'm going to lose all my elevation and get it back again. But the CDF shape is an example of something that once you start up, you're never going to fall down, you're never going to drop down again. I don't know if that's, to me it's interesting, like from the outdoor experience. Me riding my bike here from my house, which is only 2 miles away, I come down Union Boulevard racing like crazy over 25 miles an hour, which is on a bike is kind of fast, a little bit scary. I mean on a bicycle, not a motorcycle. Then I hit the hill down underneath the Union Austin Bluffs interchange there, go through a tunnel, and then I start climbing and climb pretty steadily, climb very steadily, and then I'm on the campus, but then I ride the road behind the campus. I climb extra high, and then I drop back down again and race again, and then I plateau behind the engineering building and then start downhill to get to where I park my bike. But I would rather not have to do all those ups and downs. Yeah, they're fun, but I'd rather just have a nice steady climb and then be here. If you park in the parking lots, you're essentially always climbing, I guess, but sometimes not, to get to the engineering building. But if you park in the gravel lot or ride the bus or something, I'm just curious.
Whichever one it is where you turn left and are in front of kind of the clock tower. I don't know what that's called.
Okay. Yeah, that's strictly climbing. I'm just thinking there's many routes you can walk up here and you end up having to do the same thing I do on the bike, and that is go uphill and then downhill.
I live west of 25, so it's mostly climbing up.
Okay. the types of things that we'll be doing in digital modulation theory too, because we'll be looking at decision regions for symbols, and statistical decision theory lies behind all of this. Statistical decision theory is the origins of machine learning and classifiers. I don't know, you guys being electrical engineering background know that machine learning is not just something that started from scratch about 5 years ago or something like that. It has deep roots in a lot of statistical modeling, and electrical engineering has traditionally had estimation theory and detection theory. And we do things in electrical engineering that machine learning took off from and does other things, but they still fundamentally do classifiers, which is decision making, and estimators, which is some regression technique or something like that. I think we do estimation theory better, but I don't know. I teach that class in the spring, statistical signal processing, and it's got the classical detection theory and estimation theory built into it. At any rate, this problem is just saying find the probability that x plus y is less than or equal to 1. And when you have a problem like this, and we'll have different shaped regions in the, when we start digital modulation theory. This one is just saying, okay, let's find probability x plus y is less than or equal to 1. So the first thing that you would do is that's going to form a boundary. X plus y cannot go greater than 1, so you draw that boundary out. That's the line x plus y equals 1. And then you look at the support region for this joint PDF. It's the square. And so the shaded region there is the region that has to be integrated to get this probability. And I've shown it with dx and dy. So I've shown essentially a vertical strip or a horizontal strip, because that takes me back to calculus when you learn about integrating over regions. So you get your choice and how you want to do it. I'm going to do dx is the inner variable of integration, and then dy is the outer variable of integration. So I just set the integral up. I'm going to so if I'm going to do it in that fashion, though, the upper bound, when I'm doing dx, is of course going to be the point on the x-axis, which would be right out over here. Just rearranging the equation, that's where x is equal to 1 minus y. And then I'll do the y later. So I guess this is horizontal strips. You know that, because I know you took your class in the U.S. Is that the same way you'd look at it from your background?
No.
I mean, I think calculus is pretty universal, but I always wonder, does it get translated somehow or another? And of course, younger students are like, I don't need to do this. When am I going to ever do this? I mean, I've taught fields and waves. There's a lot of volumes and 3D stuff in there. Statistics, joint or multivariate stuff. We have to do that, and it's just something that gets embedded in your brain and you don't forget it. And if you forgot a little bit of it, then you start practicing it again. So we do the joint double integration and come up with 1/3. We might do, I'm trying to remember if there's a homework problem way down the line. I think there is, way into modulation theory, where you're going to do some calculations for a probability that will be tricky. It might, I think it involves numerical integration. And then you can run a Monte Carlo simulation if you wanted to, where you just count the events that lie in that region and then form that ratio of the number of favorable outcomes divided by the total number of outcomes you generated, and then compare that to the numerical integration. Okay, other definitions, conditional PDFs. We had conditional probabilities, so now we have conditional PDFs, and we also have Bayes' rule. So conditional PDF would be a PDF on some random variable y given x is already taken on a value. So that's the joint PDF over the marginal PDF, and same for conditioning the opposite direction, and then you can spin it around to get a conditional PDF on one pair, y given x, in terms of x given y, and then random variable y over random variable x. That gets utilized in solving problems as well. And then this gives rise to just extending the definition of independence for probability to independence for random variables to say that if we have independent random variable pairs, then the joint CDF is the product of the CDF, same for the PDF. So I would say if there's anything that gets used a lot out into the future, it would be this, when it's possible. I mean, independence is used a lot in modeling, but you just don't drop down independence and say, I'm going to start assuming independence, because it may be totally wrong. And when you have correlation between random variables, and that's what we're getting into pretty quickly here, then the independence would destroy that, and you would get wrong answers. This is just a nice assumption if you can make it, because it generally simplifies things a lot. Okay, the next topic is one that is fun and tedious, but I want to talk about it. It does show up from time to time. It doesn't show up as much as it does in certain other classes, but we'll kind of carry this through transformation of random variables. So the idea that we're going to have a new random variable y is a function of a random variable x. So now we're kind of back to one-dimensional random variables, but there's a connection in here that we'll start looking at too. We'll look at one function of two random variables and then two functions of two random variables, and everything just starts kind of getting mixed up here. So there's various ways of getting the PDF on y, but probably the best and most popular method is known as the PDF method, and in the book by Papoulis that I used to teach out of for random processes, he has this theorem, and Dr. Ziemer has the theorem in his book too, says that the PDF on y is the sum of the PDFs on x, where x is replaced by a particular root, and the term root here means local inverse. So when it says real roots, what you're doing is you're finding a local inverse, a way of inverting y is equal to g of x, such that you can write x in terms of y. And the idea of the local inverse just means it only holds maybe for a certain region of x. And a good example would be the parabola. If y is equal to x squared, then the local one of the local inverses is x is equal, or y is equal to x squared, so x equals the square root of x, or y equals, say that right, y equals the square root of x, and then you can, no, I got that backwards, x equals the square root of y, and then if you have the negative x-axis, that's another local inverse that says y equals, or x equals minus the square root of y, right? Sound right? So that's what I mean by local inverse. The number of roots has everything to do with the function. And then the g prime is the derivative of the transformation function with, again, the local inverse plugged into it. And then there's an extra add-on to this saying if for some values of y there are no real roots, so that it equals 0, that inverse equals 0, then for these values there's no probability carried from the x-axis to the y-axis. And secondly, if the transformation function is a constant for some interval, then that's telling us that we end up having an impulse in the y random variable, because a lump of probability, a region of the x-axis, is all mapped into the same point, giving a constant value to a constant value in the y-axis, and so you represent that with the delta function right here. This is the picture of what's going on. If you just draw this g of x as a squiggle, then you say, how does probability, and you draw the PDF beneath that transformation function on x, and then up to the side and turn 90 degrees, you draw the PDF on y, and then you can see how this theorem makes sense. You've got the local inverses, and the way the picture is drawn here, there's 3 local inverses on one interval of the y-axis, and then you get the contributions from, these regions in here, all contributing to that region in there. And if the slope happens to be negative, then you have to take that into account with a minus sign, and that's the reason why you've got an absolute value that shows up in over here. Oops. That's so that the probability mapping is positive, because probability is non-negative. So and then you can get other parts from the picture. We'll look at some examples now, though. So this just is from the picture. Then you say, the interval is some dx times the probability f of x, and then that equates over to, not dx, but dxi, the root, and then that's equivalent to f of y dy when you take all the contributions into account, and then that's kind of the hand-waving proof of the theorem. Okay, standard example, and one that gets utilized a fair amount, is linear transformation. So g of x is ax plus b. You go in and then look at this function and say, okay, what is the derivative of the function and what's the root of the function? So, the root is x is equal to the one and only root of the linear transformation is y minus b over a, and then you differentiate with respect to x and plug in that local inverse y minus b over a, plug that in, and then you get a for the slope of the transformation, and then that gives you the equation to say what's the density on y given the density on x, and then the 2 constants that are in the transformation, a and b, show up inside of there. So suppose you had a Gaussian random variable x that had mean, and I haven't defined mean yet, even though I know you know what it is, because moments comes up a little bit later, but it has parameter mu x and sigma x squared. Plug that into this equation up above to get the density on y, and by doing some substitutions, then you conclude that, namely with this substitution and this substitution, that the mathematical form of the PDF on y is also Gaussian, and then store that in our brains for forever now, and saying that a linear transformation of a normal or Gaussian is Gaussian. It's one of those beautiful things in probability theory. It doesn't hold for very many types of random variables that you can transform them and get the same type. Uniform, it also holds for uniform. So that's the second example here, and this is, suppose x is uniform on 0 and 2, and a and b are 2 and 10. So we could go through the theorem, and that's kind of what I did at the top bullet there. But when you have a uniform random variable, I think you're more apt to just do this one in your head and say, okay, uniform on 0 and 2, the transformation is going to, the offset is 10, and the gain scale factor is 2, So you just draw this picture the way I've drawn it, and you say, okay, I'm going to translate by 10, and then I'm going to stretch by a factor of 2. And then you say, what is the height of the PDF in that region? It has, probability has to be conserved under the transformation. So if you have a PDF, you've got an area of 1 on X, and you have to have an area of 1 on Y, so you can just adjust this accordingly. I was thinking I'd go do something in Python, but I'm going to wait a minute. Because another thing you can do with any of these things is you can go off and verify them. Just sort of do a quick little simulation in Python, let's say, and just see that, yes, these things are holding. A third example is the half-wave rectifier. And this is a circuit theory kind of idea, but the fact that you have a half-wave rectifier or something that has this transformation is just coincidental. If you weren't electrical engineers, you would think half-wave rectifier sounds silly, and I think in neural networks, this has another name, right? I can't remember which nonlinearity this rectified unit, is that right? ReLU, or let's see.
Sometimes they're called a ramp function.
Yeah, I call it a RAND function, but in a neural network,
I know.
they have, okay, you don't, okay. Have you had neural networks anywhere? ReLU is ReLU, right?
Yeah.
And isn't that this function? Rectified
Yes, exactly.
linear unit, is that what it stands for? I'm trying to remember, ReLU. I have a PhD student that's using,
ReLU.
yeah, ReLU. I have a PhD student who's using this in his deep learning stuff for his hearing. I think I described a little bit about biomimetic sensing, or how we hear with two sensors, and we have head-related transfer function, head-related impulse response. So he's trying to map the catalog of head-related impulse responses that are in a database, or actually there's databases in different locations around the world. And then he's developed deep learning neural network solution to say, okay, if I know the measurements, I gotta think what the word is I'm thinking of. Anthropometrics, think of that word, it's a biology word, or human physiology. Anthropometrics refer to measurements on the body. So for his exploration and study, it's measurements related to the head, the neck, the mean radius of the head, the earlobe, all the other measurements in here. So his idea, and the idea that he's been working on, is you take measurements now of my head or of his head, and then you plug that into his deep learning model, and then it will tell you, it will form an estimate to the HRTF based just on this database and the learning extension. And then he's comparing that to the 3D modeling in using COMSOL multiphysics, where you do a wave equation solution, you get the same thing. Why was that of interest? Well, when he started, the interest was everybody should have their personalized head-related transfer function. It might help in the design of a hearing aid fit. It might be something you want to use in a gaming system. Does that make sense? The gaming system idea is we have 3D audio, so you have spatial audio and plug that in.
Right.
I got sidetracked because I said that means something else, and that's in the neural solution. At any rate, this function, its range is 0 to infinity on the y-axis. So this is a case where you have a constant value for y less than 0, and that is going to be a mapping, then all the probability on the x-axis that exists for x less than 0 is going to be mapped to a point of y equals 0. Otherwise, it's just a simple linear transformation. So this is how that works out pictorially, and then the math is just about that. You have the density on x maps identically to the positive y-axis, and then the negative, the probability that lies in the negative x-axis is that delta function at 0. A fourth one, square law device, y is equal to x squared or y is equal to ax squared. This one you can just carry on through the fundamental theorem, and then you have two pieces to put this together. Now, if we take something like a squaring device, we think of a squaring operation as, a nonlinearity in signals and systems. So you put the Gaussian PDF into this, for example, it's not going to be Gaussian. It does not come out Gaussian in this case because of the nonlinearity. And what's pretty obvious right here is that is definitely nonlinear sitting in the denominator, and then you also have the square root sitting up in there. And square law devices are used for power detectors in signals and systems. And why do we care about power detectors? We want a gain level. We want to have automatic gain control, some means of regulating the amplitude of a signal that's going into an A to D converter in a digitizer, which would be a function in a receiver. You got to match the dynamic range of the input into the A to D. So, but maybe this is the fact that we want to model the statistics of that is not maybe that big of a deal where we need to go to this level. Okay, one last transformation before we move on to two random variables. This is a special one, and it's special to me because when I took my PhD comprehensive, back in the era when I was getting my PhD, you didn't simply write a paper and present your dissertation idea to your committee. You had to stand in front of your committee. Well, you had to do two things. You had to take a written, oral, or some exam from each committee member, and then you had to go through an oral grilling session where you would stand at the board and they would be sitting out there and they would fire you questions and just say, do this, and they would just went back and forth, up and down the line, just making you do stuff. And this was one of my problems, and I didn't remember this problem. I was supposed to remember it, so I messed it up. I didn't get it right. It didn't matter. I mean, I still passed, but the point is that anything that you learn in your life the hard way, like by not getting it right the first time, you're never going to forget it after that because it bothers you so much that I messed up, because my professor that taught me from Papoulas, the random processes and in-depth random variable stuff, he was a fan of this one, so it made me a fan of it. But, it also has another value. It has other value that I'm going to point out here. So we have a function where we let the transformation function g of x be the CDF on the random variable. And what that does is it's called histogram equalization in image processing, but it makes the PDF on the output random variable be uniform on the interval 0, 1. And the proof of it lies in just saying, okay, we'll use this fundamental theorem. We know that the CDF is a monotonic function, so it's going to have a single root, and that single root happens to be the inverse CDF. So, and then if we go and carry out the derivative of the g function, it's just the PDF itself on x. Then put that together in the theorem, and we've got the proof that when you take the absolute value, which of a non-negative function is just that same function, so we get the 1, and the interval support is 0 to 1 because that's the character of a CDF. A CDF, the values a CDF takes on is always 0 to 1, right?
Is this, maybe I'm off base here, but is this related to doing inverse sampling transformation, where you use like a lookup table to go from a uniform variable to.
Yeah, exactly.
Can you
Yeah.
talk about that a little bit?
Yeah, it's right here, actually.
Oh, okay.
There's a picture of it. It's right here. Yeah, you hit the nail on the head. So this is where I've used it more often than not. I'm not an image processing person, but, you know, if you have Photoshop or you take pictures a lot, you can equalize, bring the balance into equalization. So the darks and the lights kind of all become uniform. And I don't know if that's always the best. My wife's more the photographer in my family, but the idea that I've used more often than not is I start with the primitives that are usually part of the compiler, or the C++ standard library has a lot of different random variables. But in the beginning, when I was doing this, I just relied on one and only one random variable generator, and that was the uniform one.
Mhm.
And that's what you're thinking of probably, right?
Yeah, I've seen like implementations of this in hardware even where
Yeah.
you program up like a lookup table because it's much easier to make uniform bits than non-uniform bits.
Yeah. I worked for one of the companies I worked for, not on my sabbatical, I was working as a consultant initially. They wanted to be able to generate Gaussian random numbers in phase and quadrature for digital communications testing, and they wanted to be able to do it really, really fast. They wanted it ultimately in FPGA is what they were wanting to do, and I ended up reading a bunch of papers on how to do this. I ended up getting involved with a set of libraries called the Intel, let's see, I'm trying to think, is it performance primitives? Do you ever use any of the Intel libraries for C or C++? It was something it had PP in it. It was something that you would write your code and it would compile with full optimization and be really, really fast. And then I looked at some other
There's
techniques.
Also like Box-Muller transform.
Yeah,
that
exactly.
simplifies.
It's related to this. We haven't gotten the transformation that you put together. This idea right here just tells you how to get an arbitrary random variable distribution from the uniform. So that's, we're taking this pathway right here. And the Box-Muller method utilizes that. So what you have to be able to do is inverse transform this, and so we have to form the inverse CDF. And if you want to get a Gaussian from this, this is not an easy calculation because it involves the error function, which is a numerical integration, or maybe it's a lookup table if you did it that way. But then there's another way around that, and that's what we're going to get into here next. So it's a combination of techniques that lets you get there from this. So however you want to remember it, one way or the other way. I have it in my course notes here because I never wanted to forget that after I got zinged really bad in front of my committee. But like I said, I passed. My peer, good friend, who had a committee that was, my committee had, between our two dissertation committees, we had one faculty member difference. We had the same advisor, but he had a control systems professor, and I had a statistical signal processing professor instead. So I passed. His exam, I think, was a couple hours after mine on the same day. I went home to I lived in a mobile home, a trailer in central Missouri, and I just kind of spaced out for a while. I was like, this is over with. I don't have to do this ever again in my life. This is like a ritual. He went home, as I found out later, with an assignment that he had to go do something because he disappointed one of his committee members, and he had to make something up. And it might have been on modern control or something like that he messed up. And that's the class you're in right now, isn't it?
Yep.
So I just like anything in life. I mean, you just go forward. This is what happened to me. It's me. I don't worry that much about my peer, but He probably picked on me for not having the same problem he did. He was very upset, though, is all I know. But it took a few days for me to even learn about that. So one function of two random variables could be just summing random variables, it could be multiplying them, it could be all kinds of different operations that would get involved. So it's just z is equal to g of x and y in this case. And there is a fundamental theorem approach for this, but it requires you to have n random variables going into n random variables. And then what you have to do is get the marginal PDF by integrating out the unwanted random variables. So I'm not really going to go into that, but I am going to say that a classical technique, though, that also works for one random variable from two is the so-called CDF method. And the CDF method just says we're going to look at the CDF on this new random variable. Let's see. And that's going to be the probability that the function g of x and y is less than or equal to little z, and z is the, little z are the values that the random variable can take on. So we integrate over some region in the xy plane then that's going to correspond to being less than or equal to z. And then when you get that CDF, then you differentiate it to get to the PDF. So this is a classical example, the sum of two random variables. This shows up a lot in signal processing where you have signal plus noise. You might just have two different measurements combining to form a new measurement, or maybe n measurements. I mean, it turns out that the n-dimensional case is actually pretty popular too, and it's a statistical processing discussion you can have. Like a meter, a digital voltmeter will take lots of measurements per second. If you ever cared about the PDF, this would help us head in that direction, but generally people use the central limit theorem when you get a lot of measurements involved. We're not formally talking about that, but you should remember the central limit theorem just says if you have a bunch of random variates and you sum them all together, and the means and the variances of all the constituent random variables are well behaved, like the means are all, kind of in the same region, not extreme values like plus or minus infinity, and the variances are kind of well behaved, then the mean on the new random variable is the sum of the means, and the variance on the new random variable is the sum of the variances. And the assumption in the central limit theorem would be that you have independent random variables. So, and it's Gaussian on top of that. So all those things kind of come together. So to do this problem, we again, kind of like the earlier example of the region for the probability, this is now open as x and y go back to minus infinity each. So we have this line, z is equal to x plus y, or you can rearrange it into one of those two forms, and then you can set up your integral to get the CDF, and you just have to integrate that shaded region. We can do the horizontal strips or the vertical strips again. So I put in dummy variables for x and y. I called it u and v, and then I'm integrating u first, which is x, so I'm integrating x from minus infinity up to z minus y, so that means I was using that form for the horizontal strip idea again. Integrate that and have this double integral, but then we've set the problem up, so at this point we can just stop right here. We don't actually carry out any more integration. We just say, okay, we have the limit set properly, so we know that's going to give us the CDF, and now we immediately press on with getting the derivative of that with respect to z, and this is a nice result from calculus, Leibniz rule for differentiating integrals where you kind of have this general result. And admittedly, undergraduate calculus maybe doesn't do this, but if you go out and get a math handbook or something like that, I didn't bring mine down here, it's in there if you're taking advanced calculus, which I did in real analysis. I did that kind of stuff for my doctorate. Does Dr. Semiari have you taken any math classes? Okay. I usually have my students take at least some math class just because I want them to go that way. And we have a small program, so who knows, you may decide to do that just because you want to get a class over with and you don't know what else to take from ECE. Yeah, because you have your options, ECE, computer science, highly likely, mechanical engineering, probably not real likely that you'd want to go take one there, but then mathematics has some nice classes. They have some nice advanced statistics. They have advanced calculus. They have complex variable theory and things like that.
I was thinking about taking complex analysis and
Yeah, I did it for my master's degree because I was in a program that was very small. I really enjoyed the class.
so I'm doing so much DSP and there's just a lot of hand waving with Laplace transforms and Fourier transforms.
Mm-hmm.
So
It won't have the transform theory as much as it will have just basic.
well, what's the name of it? The contour integral.
Yeah, Cauchy's integral formulas.
That's what I mean.
Yeah,
Like a
no.
lot of the transform tables will say,
Do contour
just believe
integration.
this unless you know.
Well, in my DSP notes, though, I do have it in there because it used to be in the books, but yeah, you're right. So you
It's
actually,
not in undergrad DSP books anymore. It just says, if you
Yeah.
want to derive this, have
it's still in my notes, though. It's in the back of one of my chapter 3 notes that are up on the website. But yeah, you're right.
Maybe I'll take a look at that.
Yeah, it's in there. It's powerful. And you learn about it firsthand in that class. That's the only class I've taken where they taught you about Cauchy's integral formulas and things like that, complex variable theory.
So the thing of taking it just for that reason. And
Yeah, that's-
anything else I get is extra.
Yeah, and it's good. It's actually really good. I'd recommend it. At any rate, this is the way the formula works. So if you want to get the derivative of some integral of a function, and this is very general, it's saying you're differentiating with respect to alpha this integral of a function that contains as an argument a parameter alpha, and the upper and lower limits could actually be a function of alpha too. So we've got all the cases handled, and for this problem over here, it's not quite as robust as that, but we do have the variable of differentiation showing up in at least the upper limit, and because we have a double integral in this problem, we actually have to apply Leibniz rule twice. Does that make sense, right? You first have to do it to the inner integral. Well, you start at the outer integral and then you move inside from there, and that's what I've done here. So now we'll apply it to the outer integral, and so you move it inside, and you've got these 3 components. For the outer integral, the limits are minus and plus infinity, so the second 2 terms don't contribute because there's nothing to differentiate there. So you just move the differentiation inside, and formally that's supposed to be a partial with respect to alpha. I didn't actually write it that way, but I guess if you wanted to follow the directions, that would be a partial. But now we're going to essentially starting over, and we're saying, okay, now we have this inner integral, and now we do have to consider the terms we're going to have. So we move the differentiation inside the integral, and in this case, what term do we have? So we look at what we've got. Which terms do we have from this Leibniz rule? If we try to differentiate the integrand, there's no alpha in there, there's no z in there, right? So this term is not present. If we want to deal with the lower limit is infinity, so this term is not present. So that's the term that we are going to use. So we still have the outer integral there, minus to plus infinity, and then f of y and z, we replace x by that upper limit, which in this case is just alpha itself, z minus y, and then the derivative of that function that's just equal to 1, right? So that just sort of goes away, and then we're left with the first answer. And if you would have differentiated, or if you would have set the problem up to do the opposite order, you would have gotten this other form. So I'm just showing two answers here. So that's the PDF on z is equal to x plus y. But now if we take and invoke an independence assumption, then we can write that joint PDF as the product of the marginal PDFs, and then this becomes the convolution integral. And this is a blue boxed equation because this is a fundamental result to just say that when you add signals together and their PDFs are independent, then the PDF is going to be the convolution of the PDFs. And you have a homework problem on this. The homework problem is actually, it just follows directly from this example right here. So here here I'm adding two uniforms, and then I get the PDF on the sum as this triangle, because that's what you get when you convolve a rectangle with a triangle, right? So I guess I'm just going to jump over here for a second since I've got this written up in here. So this example appeared in the notes from 2 weeks ago, but I'm just wanting to momentarily stop along in here. This was just in order to generate a plot of this cumulative probability when we were looking at random bit patterns. So this is just a numerical analysis, or evaluation of this equation, and then letting the upper limit go to infinity. So I'm summing from k equals 2 up to some value n, and then n, I think that's what I'm varying. Okay. So I'm summing k in this case, and just show that it approaches 1. But the only reason why I want to stop here is I just wanted to point out that if you're not familiar with using Python to do looping, that the enumerate function is very helpful. So let me just put that in here. I'm just doing Shift Tab when I'm sitting inside that function, and then you can just see what enumerate is trying to do, and this just tells you what it's going to do. It's going to get two lists coming out of that single input list or array, ND array if it's a NumPy array. But the first, it returns this tuple, and a tuple is a two-element immutable list. So the first argument is just the index that it's accessing, and then the second one is the value of held at that index. Very, very handy. You don't have to do it this way. You can always just say for. If you wanted to, I could have said, and up here I could have just said for k index in range, and then put the length of k in here. And then I would have just gotten an index out as I looped around. But this gives you the advantage that you get 2 for 1. So you've got both of them happening at the same time. You don't have to go try to create that. And just a little sales pitch. This document was written for people new to Python, and one thing about using Python as we use it all the way through this class is I rely on your MATLAB background, assuming you started in MATLAB. If you didn't start in MATLAB and you just started in Python, then I'm saying stuff that you don't need to know, but just in case. One of the things, though, that if you just start using Python with NumPy, you have all this great vectorization capability, and Matplotlib is very much like the graphics of MATLAB. So you're not really forced to learn as much about Python in the very beginning, but then pretty soon it's like, well, how do I do this or how do I do that in Python? So you need to know something about the language. So I wrote this document, and this document, this was written, it's in a Jupyter Notebook, which is there underneath that link, but so I used Typora to produce it. But so I start this document off with a lot of introduction on different ways of running Python, either in the terminal or in a Qt console window, and then of course in the notebook. But the case we were just looking at, if I go back up here, I start with what I call before NumPy. So before NumPy means you're going to learn about Python as if you didn't even know NumPy. You just wanted to understand how this language works. It's not a really complicated language in terms of the basic structures, looping, the data types, lists, tuples, all kinds of cool things. And so you can refer to this if you want to. So the one we were just looking at was for loops. And of course, intimately with flow control is if, elif, and else, but if you go for loops, and then I have a subset inside of this heading called getting 2 for 1 by using enumerate. So if you want to go look at anything, you feel free to go take a look at it. This would be one way of getting it, and then this is the idea of what I call getting 2 for 1 with the enumerate. And a lot of other things are in here. In terms of the way we use Python, though, just in case, I also go through object-oriented, but the fundamental reason why I'm using Python is NumPy. If NumPy did not exist, I don't think Python would have been attractive to me at all. And as a matter of fact, I did a sabbatical at Kratos, which was then called RT Logic. The first day I was on the job, well, they bought me a seat of MATLAB, they bought me toolboxes, they bought me whatever I wanted from the MathWorks. Spent a lot of money on me just to get me a fast computer and get a nice seat of MATLAB. And I had an engineer come up to me one day because they were using Python for testing the hardware in the lab. They were using Python scripts a lot, and I knew our students were learning Python if ever they did internships there. And I thought Python is for scripting and for controlling instruments and doing, validating tests of hardware and things that are going to be sold to the customer. This guy came up to me and he said, "Do you think Python will ever replace you using MATLAB in your modeling and simulation?" And I said, "I don't think so," but I didn't know anything at that point, and I didn't know still for many years after that. So it wasn't until I was working for yet another company and I started exploring it, not for NumPy initially. I needed to do nice graphics, and I was using Octave, the free version of MATLAB, and the graphics were NuPlot, and I wasn't really happy with the control. So I started looking at Python, and I found Matplotlib, and I would export stuff from Octave into MATLAB or into Python and use Matplotlib. And of course, I started getting introduced to the ND array at that time. I mean, everything you learn in life beyond school, you learn for a reason, and you learn little bits and pieces, so your angle into the box of stuff might be very specialized. And my story is like that. I mean, now if I was to start over again, I would have done it differently, but I can't. I did what I did for the reasons I did them,
So
so.
you'd write IO from Octave and read it into Plotted?
Yeah, but see, there's a class in SciPy for working mat files in, so I could write a mat file from MATLAB, and then I could open that in Python.
Oh, okay.
So, yeah, it was pretty transparent, but I had to write some helpers and things. None of my coworkers knew what I was doing, but I was working, at that time, I was now working for a company that although they used MATLAB for signal processing, they used Python an awful lot for their software-defined radio framework that was a bunch of C++ modules that they still use for their soft modems, as they call them. So Python was kind of like an upper-level language. I think it's kind of like GNU Radio, which has been out there for quite a while. You've heard of GNU Radio probably.
Yeah.
And so I went to presentations with the Air Force and did all kinds of stuff, and my coworker at that time is my boss, the other company I'm working at right now. We just met on the job because he was a consultant brought in, I was a consultant brought in, we worked as a team. But he always thought I had really nice plots, and I said, well, I'm using Python, and that was all I was doing because this was a project. Another thing, I'm just kind of getting off on a bit of a tangent, but another thing about industry work is that for this particular contract, there were two main requirements that the customer had. All the documentation and work had to be done using Microsoft Office products, PowerPoint, Word, and so on. And all modeling and simulation had to be done in MATLAB. That was just a requirement that they had. So we had to deliver stuff in that fashion. I didn't argue with that, but I didn't have a seat of MATLAB, and I didn't want to connect to a server, so that's why I used Octave. So at any rate, I just thought I'd give you can go look in here and just see a little bit what's inside of an ND array. Very powerful in Python. And it was created in the early 2000s. It was a dissertation of one gentleman who started working for Enthought Python down in UT Austin area in Austin, Texas. And then he eventually formed another company called Anaconda, which eventually developed the Anaconda distribution and the Conda tool and all that stuff. He left that company and started another company, and I think he's left that company. I don't know where he's at right now. His name is Travis Oliphant. He's a celebrity, though, to me, because he's the founder of NumPy, and NumPy actually precedes SciPy. SciPy is a bunch of packages like SciPy Stats, SciPy Signal, but NumPy sits underneath that, and then at the same time another guy wrote the Matplotlib graphics library, and those three things together formed what was originally called the SciPy stack. The guy that wrote the graphics library developed a form of cancer, I can't remember, but it took his life within the last 10 years. So he's no longer around, but there's a team that maintains Matplotlib too. And then since then, there's a lot of other graphics libraries out there, but it's still a very good one. It's one I prefer just because it's so well integrated. I've tried other ones, and they have good features, but I keep coming back to that one. It works pretty nice. I think it works better than MATLAB's graphics in a lot of ways, but the way scientific notation goes in there in plots and stuff, it's pretty nice. But NumPy array is known as an ND array, n-dimensional array, and it holds all this information. Everything in Python is object-oriented, so you have attributes like the data type, you have the dimension, how many dimensions you have, and then you have the number of elements per dimension, then you have strides, then you have the data itself. So this just gives you a picture of what is inside of the ND array. And then these are the standard data types that that you can use within an ND array. And the ones that I have in the tan or orange color are the default ones. When you declare something without a decimal point, it's going to automatically be instantiated in your workspace as an int 64, and that's similar to what MATLAB does. And if you put a decimal point on the array type, it will be a float 64, and if you make it complex by having 1J or something with a J in it, it'll become a complex 128. Big, fat numbers. But you can always cast things, or you can create things on the fly to be different types. So this has a lot of examples in there. Just thought I'd point that out, though, that it's there. So what I wanted to do over here.
Can I maybe mention something?
Pardon me?
Can I maybe mention something?
Sure.
I know NumPy, like, when you make an array, instead of filling it with zeros or ones or something, you can also, I think, declare it as empty, and that'll basically allocate memory, but just leave it in garbage, and that can sometimes be a lot faster.
So my idea of giving it zeros is not as good as just doing what, square brackets, or?
No, there's like a specific function that like gives you, it says like allocate an array of like size 1,000, but don't initialize it at all.
Okay, so let's just take an example.
It's
This is the constructor, right, array. So does it start from there, or does it start somewhere else?
I think it's array dot empty. 1,000.
Let's just see. Okay. I mean, I fell into habits from the very beginning because I was just trying to utilize what I knew from MATLAB already to try to learn everything. And I think that's logical for all of us. I tried to do that in Julia, for example, and Julia hit the wall just about with everything. If you don't know it, you can Slack message it to me or put it on the channel
Yeah.
for the class.
It's in my homework I sent you. I used it in a few places.
Okay,
So whatever it is, it's that.
okay,
But I had this thing at work where I was like making arrays that were like close to 10 million elements, and the dot zeros would just take for no good reason. Or if you start with a list and you go append, 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 append.
yeah, that
That
definitely is
also
slow.
takes forever.
Yeah, that's different. Lists are not very fast at all. So I want you to use ND arrays, and if you're new to using Python, don't go down the path of using lists. Lists are fundamental to Python, and you do use them. Small in size, they're very handy, but
They're awful for any
Speed.
performance.
yeah, I had a student one semester when I first started using Python who never looked at using NumPy or anything. He used lists for everything, and I would just beat on him when I graded his papers, and I said, why are you doing all this? You've got NumPy readily available, and it does it faster.
NumPy is like a thin wrapper around C bindings.
Right,
It's like, I don't know if you've explored this, but you can compile C and you can then create bindings to your C functions from Python.
yeah, I did take a class, well, I've not done a lot of that, but I did take Python. I explored the use of Python for a while.
But so NumPy is all written like that. I think SciPy is not all written in C. I think some SciPy functions are pretty slow.
Okay. Well, I know in my DSP class, we're using PyAudio Helper, which is a module I created that sits on top of PyAudio. And the problem with getting PyAudio put on a version of Python, and this holds true in other libraries too, is that you have to have these binaries called wheel files or WHL files. And wheel files are specific to your operating system.
Yeah, and your libc and well, I guess it depends on if they're statically linked or not, but yeah.
If it's a dynamically linked library though, right? I mean, I think in most of the cases for
Yeah,
wheels.
so it also depends on like glibc and all that fun stuff.
Yeah, and when you get onto the Windows side, that's typically where things get nastier. They don't always exist. So I have a set of instructions up on my channel for the DSP class that explain how now, today, I mean, last year, 2 years ago, it just changes constantly how you have to do it, how you have to get this Pi audio on. Now is you have to actually go to a maintainer that builds wheel files for every new release of Python, and then just pull the right wheel file down and then do a pip install, and then you put my package on after that.
And they don't have C code where you can just pull it down and run make and
So people have that, I believe, but if somebody's done that, I mean, this is over on Slack. I mean, this is,
fair enough.
if you want to know where it's at, everybody can look at it. It's in DSP. This is a document I created for that class, and it talks about creating a new virtual environment in Conda, but this is what was required.
Well, it depends on the maintainer, but sometimes they'll offer source code in a make file to generate all the wheel files.
Yeah, and this guy does. The Pi Audio, which is based on port audio, bindings for port audio, was written by a guy at MIT, and this again is just an example of other things you run into. He was a student there, a PhD student, and he did all this stuff. And then people like me relied on his library to build my layer of stuff. This is the nature of open source. You build a layer,
Yeah.
and then underpinning layers, they stop maintaining, and a new version of Python comes out, and something's now broken. Wheels weren't created for all the operating systems. So I actually approached him. I just said, hey, are you going to do this ever so we can run it with a newer version? And he said, well, I'm pretty busy. I have a family. I'm taking care of my family, and I just don't do much with this anymore. But you can do it if you know how. Just go do this, this, and this. And then I stared at it for a while, and I said, somebody's got to have done that. And I searched around, and then I found this site right here. Go Hike. This guy from University of California, I think it is. So he did create, he has a lot of wheel files for Python, unofficial Windows binaries for Python extension packages, and then this just so happens to be the listing for Pi Audio, but if you take that off of there, see this long list in here? These are all the libraries that he maintains, for Windows at least, so.
That's kind of,
What's that?
that's kind of it.
Yeah, it's very kind. Of course, there's no guarantees, but, it's,
I hate
That's nice.
installing things on Windows.
Yeah. but, this tablet is what I have to teach on, so I have to get it working here, and most of my students are using Windows. I use either Linux or Mac mostly, and I just have my Macintosh because I just like that as an option, but this kind of stuff is nice to know about, so I'll be ahead of the game unless you get somewhere before me on some of these things. So I was just going to show a real quick example here of how I might just go functions of a random variable. Looks like I'm creating 100,000 samples of RAND, and RAND is uniform on 0 and 1, add it together. So here's the PDF, and I'm using HIST. You want to get in the habit of turning on the option. If I go Shift-Tab anywhere inside the argument of the HIST function, I can see what all the various options are, and I like setting density equal to true, so that way the histogram will be normalized to look like a PDF. That's important to me. So this looks like a PDF. The height is 1, the width is 1. And then if I just simply, in my calculation here, just add it together, so that's what I did down here. I formed the new one, and there's the PDF on it. And if I was to do another one, they have to be independent, so I just can't add another one in. I'd get a PDF, but I just won't get a different PDF. I suppose I just did this. I'll just go U. If I was in Geely, I could change this one cell, and then everything would propagate for me automatically. But now its width is now the sum of the width, so I have 3 uniforms of 0, 1. So just from the convolution properties, you know that when you convolve 2 finite length sequences, the duration will be the sum of the durations, and the starting point will be the sum of the starting points, and the ending point will be the sum of the ending points. That's just a convolution property. Now it's becoming parabolic because we've got 3 uniforms, and then this eventually looks more like a Gaussian PDF. This looks sort of like a bell right now, but it's not truly a bell.
You can like calculate crest factor and all those fun things. To
Okay.
see how Gaussian it is.
Okay, yeah, or other moments and things of that sort. Okay, so we'll be back at looking at this later. So 2 functions of 2 random variables. This is also useful in modulation theory, but useful in setting up simulations too. So here we've got a simple linear transformation is one that's of interest to us as a practical matter. And then polar to rectangular or rectangular to polar are also 2 transformations of interest. So in general, though, we have, say if we have a pair, we have x and y going to z and w, and then we're interested again in getting the joint PDF on z and w. And just for the example that I did here, I'm assuming that we only have one local inverse in both of the transformation functions. And if you go through what the new PDF looks like, this is just the pictorial view of it. You've got a rectangular region, say, in the XY plane, and you want to think about where does that go under the transformation in the ZW plane. So you have a simple rectangle, and then in the XY plane, and then you have, I believe what's called the generalized rectangle in the ZW plane. Again, thinking of differentials, though, it's still, it's, what does a generalized rectangle look like in an infinitesimal form? I think it's a parallelogram, if I'm not mistaken. I'm not sure, does that sound right?
I think so.
So you can find the area of it pretty easily. But the idea here is that what happens under the transformation is that an area dx dy gets transformed to this generalized rectangles area, which very exactly is the Jacobian of the transformation, is the magnitude of the Jacobian. So that's the local magnification factor, is the way I like to think of it, as a little tiny volume of probability gets mapped to another volume of probability, but it gets scaled by this local magnification factor as a result of the properties of the transformation. And that's the Jacobian that is a matrix of partials, and then you take the determinant of that. And this is shown in 2 dimensions, but this idea applies to n dimensions as well. So you have that Jacobian. If we go through a linear transformation, just a matrix transform, then it has a single inverse, which is the inverse of the 2x2 matrix, assuming that it exists. And then the Jacobian is the determinant of the transformation matrix. Plug all that stuff into, say, a jointly Gaussian PDF that's of 0 mean, just for the fun of it, 0. So the bell in 2 dimensions is sitting at 0, 0. And that's what this would be. Plug that in through our transformation here, and then do some simplifications with some new definitions. And all I'm wanting to say at this moment, because we'll look at more at this later, is that it's going to be also jointly Gaussian. It doesn't guarantee, though, under the linear transformation that it's going to be symmetrical, it's going to be actually not symmetrical in general. It's going to be ellipsoidal. The level curves of the joint PDF, rather than being circles, a bell that's symmetrical, if you slice it vertically, you'll get circles at each elevation. If you slice the transformed bell, it'll be ellipses. So that's one popular usage of it. And then converting rectangular to polar and polar to rectangular. That's these two transformations. And we can go through the Jacobian for that transformation and get 1 over r as the magnification factor. And what happens in this case, if you were to take and plug that in, if you had a Gaussian, again, that's centered at 0 and equal variance, so symmetrical and centered at 0, 0, you get this for the joint PDF, and if you go back to the marginal PDFs from here, you get the two random variables you get back out for the radius is a Rayleigh distributed, and theta, the angle, is uniformly distributed. So this is the way, taking this result here and that transformation result from uniform to any, inverse transformation from uniform to any type of RV is a way of generating Gaussian random variables. And this is the one that I'm familiar with. Is that Box-Mueller? I don't remember if that's, there's a couple that are
I think
similar.
Box-Mueller is random sampling.
Okay, I have to look it up.
I've seen this, yeah, because Rayleigh is easier to invert. That's another way to do it.
Yeah, that's the way that I've used before. So,
Or you can brute force it with center limit theorem.
yeah, and that's not good. Because what you want if you're doing a simulation is you want to take one pair of random variates in to get another pair of random variates out. And what's really nice about using this pair of equations is you take two uniforms in, one of the uniforms will produce the theta, the other one will produce the Rayleigh, and then it will go through the 2D transformation and come back out as a pair of Gaussians that will automatically be uncorrelated from each other, and uncorrelated Gaussians, we'll be studying that shortly, will become independent. So
Yeah.
then you can use that for the
Rayleigh
interfacing
is
quadrature.
Not as hard to inverse transform
Yeah, and
as a
the-
Gaussian.
yeah, so that function can be inverted right there. That CDF can be inverted, because that's what we need. We don't need the PDF, we need the inverse of the CDF, which would be integrating that to get a CDF and then having to invert it. So, yeah, you can do it. It has a natural log in it, and I think that's the only hard function is the natural log. I used that a long time ago, a lot. I started my career, well, I started as an engineer learning Fortran, because that was what I had to learn, but before I used MATLAB, I was using C and C++ all the time, so I just generated my Gaussian random variables using this technique right here. And nowadays, in C++, we have the STL for C, and that gets you a family of random number generators. It's already built into it. Okay, like I said at the beginning of class, I realized you needed some of these things for the last homework, but not extremely off the wall. Mean, first moment, just take the PDF and multiply it times the x and then integrate that, and that gives you the first moment or mean of the density. And then in blue box there, the fundamental theorem of expectation is just used everywhere, and it's used a lot in random processes. This is, you have to be able to use this to be effective at solving problems. Without it, you're just doing so much extra work when you need to get an expected value type calculation. So the way I remembered that is when I used to teach this as the undergraduate class. the book I was using also called this the rule of the unconscious statistician, which is kind of a dry humor thing, but it's like if you don't know how to get the moment of a random variable, the new random variable, and see what this is all about, the reason why I'm saying what I'm saying is so if you wanted to find the mean on x, or the mean on y, would you go through all the work of transforming the random variable x to the random variable y's PDF and then use that in the definition of the mean? You say, no to that, I don't want to do all that work. I'm going to just simply use the PDF at the input side, x, and use the transformation function, and then plug that into here. If I need to get, a simple example, if I need to get expected value of x squared, I can think of that as being a simple transformation too. That's also known as the second central moment, but fundamental theorem of expectation can be used in that case too. When you have more than one random variable and you want to get, variance is the second central moment is the name of it, because you subtract the mean from the random variable and then take the expected value of the quantity squared. So it's a second moment, but it's central or centered around 0 because you subtract the mean. And that gives you the variance, and the standard deviation is the square root of the variance. So the fundamental theorem extends to multiple random variables, and that's this line right here. And then conditional expectation is also another route to getting fundamental theorem of expectation to apply. So if this is the problem at hand, this expansion can be utilized if it makes life easier. What you're doing is the inner expectation is holding y constant as if it's a non-random quantity, and it's just a parameter that's going to carry through. And then when you get done doing that inner expectation, you've averaged over all the x's, and then you're left over with something now that's just a function of y, and then you have to integrate that out with that averaging operation. Some other quantities that come up would be correlation coefficient, covariance. So covariance is when you're correlating, is when you're finding a second moment between two random variables, second central moment. So that's the centered x and the centered y. And the correlation coefficient is just normalizing that by the variance or the standard deviation. Frequently you'll see it written with a square root here. And the correlation coefficient runs between -1 and +1. It's a measure of the angle between two random variables, if you think of random variables in an abstract vector space. So that's what correlation coefficient relates to. It's like the dot product, and it's the cosine of the angle. So if the cosine of the angle ranges between 0 and pi, or the angle ranges between 0 and pi, then the correlation coefficient ranges between -1 to +1. So 1 meaning perfectly collinear, and then -1 means that they're equal and opposite. They're anti-correlated. They're pointing in the same. They're in the same plane, but they're in different directions. And if they're orthogonal to each other, then the idea of the dot product being equal to 0 just says it's like there's no correlation between them because one doesn't project on the other. So that's the last thing down there. And there's a nice property that, uncorrelated is this property right here. This is used a lot in modeling too. It looks like independence because you're taking a product, but the product is not of the PDFs, it's the product of the expected value. So this property is less of a property than independence. What I'm saying is if you have independent random variables, then you definitely have uncorrelated. If you have uncorrelated, you don't necessarily have independent, because that's the stronger statement. But for Gaussian random variables, independence or uncorrelatedness implies independence. And that's another important thing to take advantage of. I guess I need to take the break. I thought I'd be able to get through this chapter, but I think we should take the break. It's 9:35. That clock confuses me because it's doing nothing. I should be looking at my watch or my computer. Do you have any questions before we take about a 10-minute break? Okay. Well, I'm going to pause the video here. Okay, we're going to get started again. Looked at some email, a lot of trash to get rid of always. I thought I'd just quickly go over these next couple. This is just a simple example that, no complications here. It's just I wanted to point out for uniform random variable, you know what its mean is. Its central value is just the average of the two endpoints. And when you go through the variance calculation, it's 1/12 of the width of the PDF. So for me, I always just remember it as delta squared over 12, where delta is the width of the PDF. There's alternate characterizations for random variables. One is called the characteristic function. Sometimes it's used in some modeling in development, and sometimes you would see that in papers and things if you're reading on modulation theory that somebody might have taken this route to get somewhere. And the characteristic function just ends up being closely related to the Fourier transform of the PDF. So the formal definition of it is it's the expected value of a function of the random variable x that is defined to be e to the j v times x. So you end up with the forward transform as the expected value of this function, and then the inverse Fourier transform is the getting back to the PDF. So a person might choose to work a problem in the characteristic function domain. So revisiting the problem with the sum of two random variables that are independent, then we can go about this by going into the characteristic function domain immediately. And if you then make your substitution for z as x plus y, you just simply say, okay, I'm going to try to get the PDF on z in terms of the characteristic function on z, and the simplification that would happen immediately would be to just say, okay, I can separate that expected value as the product of the expected values, and it looks like I have a typo in here. The parenthesis goes the other way. So the joint PDF is the product of the marginals, and then this thing will work for me. Breaks down into the product of the integrals, and then you have the characteristic function for each of those, and then that just is the convolution function in the frequency domain, right? Meaning it's the product of the characteristic functions, and then you would inverse transform that back to, from the convolution theorem to be the convolution of the PDFs, which is what we saw earlier. I like it. It's not something that I go to. You might want to use that point of view. I don't often think that I need to do that, but it's always available, and I've certainly seen a lot of things develop, especially when you have a lot of random variables, where the characteristic function can be helpful, just because it kind of makes things more efficient. Multivariate Gaussian random variable, this shows up fairly often in modeling, where you've got correlation between random variables, namely samples or in phase and quadrature. And what will introduce correlation is in digital communications will be filtering or memory of some sort. So in a channel model, you won't be able to say that the two multipaths are independent of one another if, as a result of correlation between the samples, right? There's a memory relationship, so you can't just say they're independent. So this is the joint PDF expanded out for jointly Gaussian, and there are there's 2 means, 2 variances, and then a correlation coefficient that's controlling this joint PDF. And so you've got a coupling between them, and then you've got the possibility of different variances. So I just took a simple look at this years ago in Mathematica, where we just have uncorrelated and then equal variance in each direction. So the level curves are the circles, like I was talking about earlier. The mean was 5 in this case, so that's why this is centered at 5. And then you start letting the correlation coefficient vary, and you start rotating. You form an ellipse immediately, but you start rotating the major axes. In this case, because the variances are equal, the major axis of the ellipse is at 45 degrees, but the minor axis is changing relative to the major axes in terms of the width. And so I flip to negative correlation coefficient. It does that. If I was to change it to a value other than 0.7, it would just make it get tighter or looser. I'm just going to go quickly back over to here. In Python, I have a function that I wrote, and I think this function could show up either on one of the exams or in another homework problem, but this is just a way of creating correlated Gaussian samples. So here, this function creates a pair of Gaussian variables, random variates, that have a mean contained in the array mean for the x and y parts, and then the array variance contains the x and y variances. Rho is the correlation coefficient, and n is the number of samples. So this just gives out a n by 2 array. So it's got each column in the array is the x and y variates, and they're statistically coupled if rho is not equal to 0. So I just generated some samples in here, and then proceeded to just do scatter plots of what we're looking at. So this was in the notes. That's the 0.7. The angle of the major axes is still 45 degrees, but now it's tighter if I draw the correlation coefficient closer together. And of course, you learn in statistics, and I think it's in the second homework problem actually too, that maybe it's not in that problem, but it's related to this, that you can predict one random variable from another if you do a regression model, and the regression line happens to be this 45-degree line, and then you can estimate a value of y from a value of x. So you would go up into here. Well, oops, I can't draw on this one because this is the web page, but if you had x and you knew the statistical properties, you could get the value of y from the fact that they're statistically coupled in that sense. And the variation is controlled by the correlation coefficient. That all makes sense, right? That line that ellipse becomes a line, so you know with extremely high confidence, essentially perfect confidence, that y is related to x. Another thing you can do that I just want to point out, because there may be a reason, and I can't think of that reason right now for a homework problem or some simulation, is that if you go into the stats package of SciPy and you go into multivariate normal, and you can, from that, you can go dot into the RVs function, and this will give you an n-dimensional random vector. So this carries it to any dimension you want. I'm just sort of looking at it since I was over in the Jupyter notebook right now. You can define an array, and then we'll have the covariance matrix. I'm about ready to define that. And then you can just say how many samples you want to generate. That's the fourth argument. So first argument is array of means. Second argument is a covariance matrix, row by row by row. And then the third argument is the number of samples you want to generate. And then here I went to the trouble of actually going into creating a 3D plot using Matplotlib, and you can look this up on the internet, but this is sort of the formalism of how to get that set up. And then I did some scaling of the axes and then created a nice scatter plot. And if I did not have this inside the notebook, or if I used a Matplotlib library function to make it a variable in the notebook, I could spin this matrix around, but I'm not doing that right now. So I could kind of examine it and as I spin the orientation, the 3 dimensions around. But to me, this picture just goes up to the 3rd dimension. So if I look at what I've got here, I've got, of all 3, I'm creating 3 3-dimensional random Gaussian vectors. One has 0 mean, one has a mean at 5, and one has a mean at 0, but it's shifted on the second coordinate to minus 7.5. So that's the green one, I believe. Yeah, green one's here. The first one is centered on 0 in 3 dimensions, and then the blue one has been shifted, and that's the one that's at 5, 5, 5 for its center. And then the covariance matrices, which describe both the variances along each of the major axes and the coupling between the axes, are described by those 3 by 3 matrices. So the first one is diagonal with 1s along the diagonal, so that's the variance on each of the components, and there's 0s elsewhere, so there's no statistical coupling between the components. Next one is 1 along the main diagonal, but there's statistical coupling between the first element, or the first dimension, and the 3rd dimension of 0.5. And a property of a covariance matrix, I think I have it in the notes here in a second, it has to be symmetric. So this is a symmetric matrix, which is the reason why you see it in 2 locations. Then the 3rd example, there's a negative correlation coefficient between the first and the second, so that's set at minus 0.5. So it's kind of hard to see from this angle. If I was to break this out of here and do it separately, then we could spin it around. And then you could kind of see that these shapes are, well, the red one is going to be a perfect sphere, right? Because there's no correlation, there's no coupling. So it's a nice cluster, say sphere. The green one is got an ellipsoidal shape to it vertically, and the blue one has got a horizontal ellipsoidal shape. Let's see. And then I can do statistics on that. I can calculate the mean of this array of random samples, which how many? I ran 1,000 only. So maybe I should run more and just see if it gets nicer looking in terms of the statistics, more well-defined. At any rate, I did the mean vector estimate on the first one, so that's the D1, 3D1, and then I did the covariance matrix estimate on 3D1, and this one has got the coupling between the first and the third, and the small values, not zero, but small values show that there's nominally zero coupling on the first and the second, and then there's ones down the diagonal. So you get there's actually a lot of information in that, right? It's not just one little number, it's all those numbers that mean something. Now I'm contemplating whether I should do something else that I could do, but don't know if I should take the time to do it. Maybe my answer is already here, because something seems to be missing. I had a terminal window open that was running a bunch of applications, managing my applications, and it seems like the terminal window disappeared, but yet it's how I launched my kernels for my Jupyter Notebook, and also had a Julia session running, so I don't know how I'm supposed to get back to that when the terminal disappeared. You know what I'm talking about? I started the terminal up and I used Microsoft's terminal application, and I had three different terminals in my session, and it's gone. Not happy with that. I don't know where it would have gone to, but it's gone. I'll investigate that later. What I was going to show you, though, is that you could, if you wanted to be able to visualize this 3D plot here, you could go outside the notebook and start up a IPython session just from the terminal, and then if you did this same plot, you would be able to get a plot window that you could spin around and visualize stuff in 3 dimensions. I won't take the time to do that right now since that terminal has gone away. So for back to the two-dimensional case, the angle is controlled by this equation right here of that ellipsoid. It's controlled by rho, and then the difference between the variances. But because I was using equal variances, that number turned out to be 45 degrees in all the cases I was showing. And then not shown here in detail is the fact that when you have statistically coupled jointly Gaussian, you get the marginal PDF. In other words, if you integrate out the unwanted random variable, you will get a PDF that's Gaussian. But it involves, wait a minute, I'm thinking of something else. I'm thinking of statistically coupled, conditional PDF. So if we went through the trouble of finding the PDF of the conditional, I think I have that a couple pages away. You'd have to form the ratio of the joint PDF divided by the marginal, and then you complete the square, and then you end up showing, actually I know it's in here, just simply, yeah. Didn't remember where it was, it's just another example I had that conditional PDFs on a jointly Gaussian PDF are also Gaussian. It's just that now the covariance or the correlation coefficient enters into that, and it depends on the value of X or Y in each of those. So the conditioning event controls the mean as you move along the x-axis, you will get a different mean shift on the conditional PDF y given x. I think I'll go back and look at where that shows up in my example, but what I wanted to say was that if you go revisit the linear transformation problem where we have a general bivariate Gaussian PDF, we go through the same thing we did before. This is the transformation. We have a matrix to transform x and y, so A, B, alpha, and beta is the way I have it defined here in the notes. And that's how you get z and w. And then there's also two other constants that control the possibility of a mean shift, c and gamma. So this is sort of a generalized problem. And this just says you can go ahead and start digging into that and saying what's going to be the mean on z, what's going to be the mean on w, what's going to be the variance on z, w, and then what's going to be the covariance between z and w. And then you can go further with that if you wanted to get the correlation coefficient, but it's going to be Gaussian all the way through. We started with that in an earlier example. This has got more frills on it because they're correlated Gaussian, forming another correlated Gaussian through a 2D transformation. It still stays Gaussian though, and this is just, I don't know, many years ago, long time ago, before your times in this world, there was, Timex made a watch, and Timex had a slogan about their watches. Have any of you ever heard of Timex watches? Okay. They were mechanical watches. I think they're now electronic, but the advertisement always was for their watches, takes a licking and keeps on ticking. So taking a licking is like it's all beat up, falls down, pick it back up again. It's still ticking, still works. So Gaussian random variable, in my mind, my analogy was it takes a licking and keeps on staying Gaussian. You just beat up a Gaussian random variable through linear stuff and it's still Gaussian. You can't make it go away, it comes back again, which is very powerful. It's very comforting actually to know that's the case. And I was going to pull up my book, but I don't have the PDF version of it. The second homework problem involves calculations that involve this set of equations here. You have to go through that in order to get the answer that they're looking for in that problem, second problem, in the homework, set number 2. So you gotta work through these details because the problem is jointly Gaussian, and then you're finding a new random variable. So it's like you're finding z. So in the homework problem it's pretty much just like this, except you've just got this piece, and then you have to get the PDF on z. That's what you're off to do, and you have to go through the pieces to carry it through. So you have the characterization of x and y, which are jointly Gaussian, and then you want to find the mean and the variance on z, and you just have to go through a series of calculations to get there, to get to that. Okay, here, this was another linear, and here's a numerical observation of that. So bivariate Gaussian before and after. It just changes its shape. It moves it around with the mean shifts and so on. So this is what I got excited about, thinking I was there, but it doesn't come up until here. If you have jointly Gaussian and you want to now form the conditional PDFs, this is also jointly Gaussian, and you get there by completing the square when you go through the definition from marginal joint over marginal gives you the conditional. So it's not immediately obvious. You have to complete the square, so you have to be bullheaded enough to drive the math all the way through, but you can complete the square, and then you will get it to be Gaussian once again, And these are the answers for that. This was an example in MATLAB. We already did that example over in Python, so don't need to look at that again. A little bit on n-dimensional random vectors. So this is just an extension from 2 up to n, and so we can define it as a random vector, usually as a column vector. The existence theorem is the same. It's a non-negative, any non-negative function of, in this case, p random variables, as long as its p-dimensional volume is 1, is a valid PDF. You can find the joint CDFs by going through the p-fold integration. You can find the probability by integrating over p dimensions. And then a little bit trickier is you can go ahead and find marginal PDFs, which in this case, now if you started off with 5 random variables, you could integrate it down to 2 or 3 or 1. All these things can be done, and that's what this is talking about, just integrating out unwanted random variables. And then you can also carry that into conditionals. So if you had 5 and you wanted to condition the first 3 on 4 and 5 being present, then you have to do this example right here where you have to go through the steps to get there. You have to take the joint on all 5 and divide it by the marginal on just the pair 4 and 5, and then that one's conditional. If you've got mutually independent, then it's the product of the PDFs, which is nice. I go through an example in here, just of going through some of those calculations. I think almost the end here is linear combinations. So this is working just with moments alone. If you don't care to work with PDFs, and very frequently we don't need the PDF, we just need to work with moments. So if we're working with a sum, linear combination of p random variables, that might be a detector quantity in some multi-channel receiver or diversity combining receiver. That's where I can think of this showing up, where you're going to have diversity combining in a channel. So then you can characterize the mean and the variance. So this is the mean on the linear combination. A little bit more complicated finding the variance on the linear combination. But when you have mutually uncorrelated, then mutually uncorrelated will mean that this term will go away. So then it's just going to be the sum of the variances with the appropriate weightings. And if the weighting factors are all equal to 1, then it's just going to be the sum of the variances. And then you can go the sample mean and sample variance, which I threw up in here. Stop on this one for a second, though. I mean, a project I worked on once at RT Logic was to build a diversity combining receiver. So how did we do that? I mean, we're not talking about channel models and digital comms just yet, but this would be behind that. If you want to do a simple diversity combining receiver, you'll want to combine all of the channels, in this case it's n, inputs in such a fashion that you can minimize the variance. So you'll want to form some sort of a weighting, right? When you combine pieces of information together, you want to emphasize the ones that have the lower variance and de-emphasize the ones that have the weaker variance. So in diversity combining, that's called maximal ratio combining. There's a name for that, MRC. And so what I had to do to help accomplish that MRC was also come up with a side algorithm that would estimate the signal to noise ratios on each of the channels, so that way you can optimally combine them. So that was an inherent part of that project, was the diversity combining wasn't gonna be that hard, but it was how to actually ratio and then estimate. And one of the challenges in that is, signal to noise ratio estimation is noisy and imperfect. So the algorithm I chose was based on some papers I read using fourth moments. And fourth moment algorithm works pretty well, but all algorithms fail if the signal to noise ratio gets too low. In other words, you'll be able to get a good estimate of the signal to noise ratio, but if it gets too close to zero, then things just start to kind of fail in general. But a communications engineer would say, well, I can cope with that to a certain extent because I don't expect all channels to be really, really bad, and the math will work out such that if one channel is really bad, you just won't use that one at all, you use the better ones. And so what's an example? Is there a wireless hub in this room? I don't see one. There's maybe one out in the hallway, but you're familiar with wireless hubs in your house. You generally have two-channel diversity combining. So that's just doing some maximal ratio between those two sources. When we get into uncorrelated receivers and processing, we'll be having things like this where we have sums of normal random variables, in that the variance will be the sum of the variances. But then we'll also have things, it's not in the notes here, where we're going to do non-coherent combining, where we'll be doing sums of squares of random variables, and that's where we get into chi-squared and those statistics. So some of those are shown in here. This is just right out of the book, showing some of the popular PDFs, and we'll bump into some of these, like chi-squared we'll bump into for sure, and non-central, both central and non-central chi-squared. Right now, the only one that we're seeing in here is central, but we'll also have non-central. And depending upon the fading model, some of these other ones come into play. So that ends this chapter. The new homework just has 2 problems from this. I'm going to close that one, and just because we don't need it right now. As I've already hinted, this will be first one is convolution, independent random variables coming together, and this one is spelling's bad. Second one is jointly Gaussian with rho not equal to 0, where you're forming something along the lines of z is equal to x plus y. And I think that's exactly what it is, but it's along those lines. But everything else is going to be random processes. And then the simulation problems down here are connected in with that. And we'll talk more about this as we get into that topic. This can be a complete course, and when I used to teach out of the Papoulas book, it was probably about half of the class, maybe a little bit less than half, because we spent so much more time on n-dimensional random variables, or just, and SSM off the books now for a long time. I taught it right into the ground. I drove it right into the ground, you might say. It used to be a required course for all master's degree students and PhD students, but of course, we assumed that they would already have it. It was a required course in communications and signal processing. It was a core course in the master's degree program, so we used it as a way of making sure we had enough students in our graduate level courses. We would say, if you're a master's student at UCCS in electrical and computer engineering, you had to take, I think, out of 5 core classes, you had to take 3 of them. So that was a way of maintaining enrollment, but over time, faculty didn't like that anymore. They didn't want their students taking these other classes. They only wanted them taking their classes. So that was working against us. And then I taught the random processes class, but people just didn't like it. They just simply did not like it a whole lot. So the enrollments just started dropping, and even people that were in communication and signal processing just didn't like it enough that they couldn't complete the class. Did you have your class that way? It was just all probability and random, all the way through random processes for a whole semester?
We take this class more than 5 years.
Okay. I mean, it was with graduate students, or just as a?
It was for graduate students.
Yeah. Well, when I was a young faculty member, that was a class I started off teaching. And I didn't have any students that I knew. I had a lot of people taking my class. They didn't like the class. We had morale problems in the class. I felt like I was just killing people with the class, but they had to take it, so. And then eventually the numbers just got smaller and smaller, and it probably died with one semester it came along, one person was in the class, and then I was told, we're not going to do this anymore. So it was a tradition, but I grew up with that tradition too. I took it at a younger age, and then, I don't know how other schools are doing it. So we have it built into certain other classes like this class, and then it's also built into a little bit is in modern DSP for discrete time random processes, and then it's also built into statistical signal processing in a more in-depth way than it is here. So what is a random process? A family of functions is the way I like to think of it, and this is the way I've always taught it. This is the way the books that I used at the time taught it. We have the underlying sample space. We have chi sub I through chi sub n as the elementary outcomes, but now each elementary outcome, when an event occurs, an experiment is run, produces a whole waveform. So we have a ensemble of waveforms, and the ensemble idea is because of the waveforms. Since I play musical instrument, play bass trombone, I think I told you that, I enjoy playing it. It is an ensemble, right? I play my musical passages, somebody else next to me plays theirs, and we form an ensemble. So that's where why the term ensemble gets utilized here. All these waveforms are possible outcomes that can occur. In the case of playing music, we're all really here, whereas the case in the ensemble idea for a random process, only one of the waveforms will appear, but any number of waveforms are possible. It could be a finite ensemble, it could be an infinite ensemble. Usually there's an infinite number, so that ... means that there's just an infinite number of possible waveforms out there. So there's typically 4 different interpretations, and when books start using random processes in modeling, whether it be a comp theory paper or a comp theory book or something along those lines, random processes can, the notation gets interpreted in one of 4 ways. We could be thinking of the ensemble of functions as an entirety, and so that's number 1, a family of time functions in both t, the horizontal axes, and all the different possible waveforms, the chi values. Or it could be a single time function, so we're just going to look at one. So just one of the waveforms out of the big stack is pulled out. So chi is fixed. And number 3, it could be a random variable where you just slice down through the ensemble and just characterize the randomness at one particular time instant. Or it could be just be one single functional value of one sample function. So when you go back up to this picture, it's supposed to be a vertical line. I didn't draw it very well, but so when we slice down like that vertically, we get a random variable. When we pick a waveform horizontally, we're just getting a function of time. We don't even think of it as a random anything. It's just a waveform. It's just like the waveform of the day, the waveform that we get. And then you could go further and just say, out of one of these waveforms, I just care about 1 point. And it's just a number. That's all it is. So how we interpret that is subject to the rest of the wording that appears in a problem. But once you know that random processes exist, you can't be ignorant and say, I just want to have a single number. You have to be open-minded about it and say it can be everything. So from here on out, if we're talking about random quantities, random processes, we actually have to think that the ensemble is being there. But if you're working in the lab and taking a measurement with test equipment, what comes to mind is going to be a single time function. It's like, this is our event, this is our day, the waveform coming out of the generator is the only waveform that's going to happen for this particular experiment, so it's just one time function. But if you think about all the possibilities, that's where the ensemble comes into play, and that's why random processes are so powerful, but also can be so confusing, because we like to think of the random variable idea when we're doing the pencil and paper and the analysis mode. We're just thinking about what's happening at this time slice, the next time slice. Whereas when you're in the lab, you're thinking of, I just have this one sample function. So we have to reconcile that, and that's why we end up with characterizations of a random process. One is statistical, and the other is the time average. And then what couples those two together is going to be this idea of ergodic properties, which says that time averages and ensemble averages can be interchanged under some understanding and under certain conditions, like it'll be ergodic in the mean, ergodic in the variance, ergodic in the autocorrelation function, and so on and so forth. And in reality, Keysight would not exist and make instruments that people cared about unless we could say these things, because you want to be able to take a measurement and then you want to go back to your analysis, the person that did the theoretical modeling of everything, which was statistically modeled based, and connect them together.
Yep.
Does that make sense to you as working for an instrument company? It just has to be that way. And consumers, the cool thing about a consumer is they don't have to care. They don't really care at all, right? They just let my device work. But us builders of things, we have to develop these understandings about how to make things work. So And of course, I'll just do this. One of the other things that comes up frequently, or is gonna come up absolutely, my pen will start working again, and it's going to be, it's not gonna work right now. Well, I was gonna do this, I can do this, I think, yeah. So a lot of the characterizations we're gonna do random processes will involve multiple time slices. So we'll sample at T1, T2. Most of the time, we're just gonna do 2 samples, but the full-up random variables view of a random process is you've got an infinite number of time samples. So x at T1, T2, and so on and so forth. If it was continuous, we can sample at the nanosecond or microsecond level. If it was discrete, we're going to be sampling at the sample indices in the system, like how the A to D has captured it. And that would be a discrete time random process. So formally, a complete description of a random process requires a joint probability density that can go up to n dimensions. And see if my pen is going to start working again. No. Sometimes I get it to work by pulling the battery out and messing around with it. Does anybody have a stylus like this? It's a quadruple A battery that's inside here, I think. I don't know. I put a new battery in when we started the semester, and I don't have a spare one on me. I have some in my office. I'm going to have to get them with me. The battery may have just died. But I have a mouse, so. I don't know what you think, but I think that's awful to think that you'd have to be confronted with an n-dimensional PDF. So what we are content, though, is to think about most of the time 1 or 2, and then we can get by with that. So to get you thinking, though, about the possibilities, I have examples in here of a couple different simple random processes. And the thing about simple random processes, they can be so simple that they actually, your brain can't capture it as well as it can a more complicated one. So that's what some of the example things do in the notes, and that's what some of the homework problems do as well. So here we have a sample function, or an ensemble that's composed of just 2 sample functions. So we're saying half the time it's sine pi t, half the time it's 2t. So this is the complete ensemble right here. And so how would we characterize the joint PDF, or the PDF of this random process? Well, we can characterize it at a single sample time, so it's the first order PDF. So all we have to do to characterize that is we just have to think about doing one slice at time t, and then we can just simply say that that first order PDF is half the time it's going to have an amplitude value, which is sine of pi t, and we can write that with a delta function of x shifted to sine pi t, so that'll give us a point on this curve at that value of t, and then the other half the time it's going to be x minus 2t to give a value on the ramp, and that's the complete PDF. And if we wanted to get a second order PDF, we'd have to do 2 samplings, but from this first order PDF we can get all the moments we want. We can get the mean, the variance, all those types of things going on. But if we want to get up to a two-dimensional PDF, then we have to sample at more than one location, and then that's where things would get more complicated. And I'm not going to do that, but I'm just going to say we would have to go over here, and then we'd have to think about what is the joint PDF going to be, and when we start writing out the joint PDF, we have to look at the statistical coupling between our sample functions, and in this case, because they're deterministic functions, then we can start writing this out, but it gets pretty messy in a really big hurry. So I'm not going to do it, but can you imagine if you had to write a joint PDF for this at sample time T1 and sample time T2, then you would end up having to do some tricky things with conditional, and the fact that if you know where this sample function is at T1, you know what it is at T2 because it's deterministically related.
I guess imagining if you have like a Gaussian noise,
Mhm.
would your ensemble then be like an infinitely long of every possible sample at every possible time, or?
That's right. So white noise is the ensemble. I think of it as running from down the center of the earth, I mean, stacked up, and the ensemble is just going up to infinity. It's just different number of combinations. This is why I'm having you work this simulation problem. It's just over randomly phased sinusoid, so it's more manageable, but you're going to have it in a NumPy 2D array, so each sample function is the row, and then you'll randomly change the phase. And I'm looking at the clock, you're saying we're going to run out of time. Just a quick, another example, this is a different way of defining a random process. This is just a function of time that also has a random parameter in it. So this one is different than the first example. Mu is got some density associated with it. So if we start drawing out the sample functions in the ensemble, it's a collection of exponentials, and then we have to think about, characterizing it. And here, to characterize this one, we can think of one function of one random variable, ideas, and then we can just sit at a particular time value right down in here, and then we can use the fundamental theorem for the 1D PDF and get that to be the PDF at any given time. And the PDF is got amplitude given by this function then. So that's starting to get a little bit mind-boggling, but the homework problem, simulation problem, is randomly phased sinusoid, and then we'll have the white noise as another standard example, but the randomly phased sinusoid is useful in comms because we have this epoch and we don't know the phase of the carrier. This would be an unmodulated carrier. We'll then extend that to the modulated carrier, but so we have the carrier frequency F naught, but then there's a random variable phi associated with it. And here I used Mathematica to draw the ensemble, but I also have it in Python. Because of the limited time, I'm just going to jump over to this other notebook, and this is on the website. I have a random processes Jupyter notebook. This one starts off drawing this ensemble, so drawing a family of waveforms at different phases, and I could think of sampling down a whole collection of waveforms to get the mean, and I could get the variance, and then we're going to get another quantity called the autocorrelation, which is going to be relating to sampling the waveform at two different time slices, and that will lead to the autocorrelation function. And so in order to create this ensemble, I've got, in this notebook, I've got some nice hints on how to generate it. You could do a two-dimensional loop, and you could just fill up an ND array in that fashion. But a more efficient way of doing it is using vector processing. So I talk about that, how you, in order to create a randomly phased sinusoid, you need to make this argument 2 pi f naught times t, so t has to vary in the horizontal direction, and then as you go down the vertical direction, the values that theta takes on is going to change in that orientation. So you're going to generate that as an n by m matrix, and both t and theta will need to be matrices, but they're going to be matrices where the time axis is going to change only with a horizontal stepping, so vertical will be identical, and then when you do the theta axis change, it's going to be constant in x, and it's going to change in the vertical axis. So I want you to think about this. I'm not giving you the answer, but here's an example of how I'm going to do that. The ampersand is NumPy's way of multiplying two matrices together. So I'm using NumPy to create a random 3 by 1, and I'm going to multiply it by a 1 by 5, and what's the rules of matrix algebra? The inner dimensions have to match, and then the new matrix is the outer dimensions, right? So this will create a 3 by 5, and then you take that up to very high order for the homework problem. And I kind of lead you through how to do that in here. So the whole waveform creation idea is in here. We're pretty much out of time now, so I'm going to have to go. We're not done yet. The clock means nothing to you, but it's 10:41, so I'm starting to pack up right now.
Okay.
Any questions before we pack up? You're going to come up to my office, but
Yeah, that makes sense.
so I'd study this notebook as well as look at the homework stuff. I mean the problems too.
The homework is due in 2 weeks, right?
Yeah, that's right.
27?
That's right.